So let's compare a boosted decision stump to a decision tree. So this is the decision tree plot that we saw in the decision tree module. So this is on a real data set. The base is based on loan applications. And we see the training error as we make the decision tree deeper tends to go down, down, and down, and we saw that. But the test error, which is kind of related to true error, goes down for a while. And you have here the best depth, which is maybe 7. But eventually it goes back up. So let's say after depth 18 over here, the training error is down to 8%, so it's really low training error, but the test error has gone up to 39%. And we observe overfitting, and in fact, we observe a huge gap here. The other thing to note, by the way, is that the best decision tree has classification error in the test set of about 34% or so. Now, let's see what happens with decision stumps but boosted on the same data set. You get a plot that looks kind of like this. You see that the training error keeps decreasing per iteration. So this is the train error. So as the theorem predicts, it decreases and the test error in this case is actually going down with iterations. So we're not observing overfitting, at least yet. And after 18 rounds of boosting, so 18 decision stumps, we have 32% test error, which is better than a decision tree gets, in fact, better than the best decision tree. And the overfitting is much lower. So this gap here is much smaller. So the gap between the training error and the test error is kind of related to that overfitting quantity that we have. Now, we said we're not observing overfitting yet, so let's run boosted stumps for more iterations and see what happens. So let's see what happens when we keep on boosting and adding more decision stumps. On the x-axis is adding more and more decision stumps and more trees, but just level 1 trees, and see what happens to the classification error. We see here that the training error keeps decreasing, just like we expected by the theorem, but the test error has stabilized. So the test performance tends to stay constant, and in fact, it stays constant for many iterations. So if I pick t anywhere in this range, we will do about the same. So any of these values for capital T would be fine. So now we've seen how boosting the test error goes down. It seems to be stabilizing, but the question is, do we observe overfitting with boosting? And in fact, we do observe overfitting with boosting, but boosting tends to be quite robust to overfitting. So if you use too many trees or too few trees, there's a huge range when it does okay. So here I'm going up to 5,000 decision stumps, which is this type of boosting that we're doing here. The best test error was about 31%, but if I kept going too far, I go to 5,000, I'm overfitting, that test error is going up, but it doesn't go up that much. It goes up to 33%, so there's some overfitting here. Very importantly, in these examples, I've been showing you the test error and talking about what happens to overfitting with boosting, but as we know, we need to be very careful of how we pick the parameters of our algorithm. So how do we pick T, capital T, which is when we stop boosting? We add 5 decision stumps, 5,000 decision stumps. And this is just like selecting the magic parameters of all sorts of machine learning algorithms. And it turns out that almost every algorithm out there, model, has a parameter that trades off complexity, depth of decision tree, number of features, or magnitude of the weights in logistic regression. And here is the number of rounds of boosting with the quality of the fit. So it's just like lambda in regularization. We can't use the training data because the training error tends to go down with iterations of boosting. So you say that T should be infinite, it should be really big. And you should never use the test data. So that's bad. I was just showing you illustrative examples, but you should never do that. So what should we do? Well, you should either use a validation set if you have a lot of data. If you have a big data set, you select a subpart of that to just pick the magic parameters. And if your data set is not a large, you should use cross-validation. And we talked in the regression course, we talked about how to use validation sets and how to use cross-validation to pick magic parameters like lambda, the depth of the decision tree, or the number of rounds of boosting, capital T.